All right, so I think we can start now. Hi, everyone. My name is Anya Grushina, and I welcome you to the second session of today's Nanofab POM conference. I hope you're all having a great time. I certainly am. And this session will consist of two tutorial talks, followed by a break and another tutorial talk. So the first tutorial talk will be given by David Norris, who is a professor of materials engineering at the Department of Mechanical and Process Engineering at ETH Zurich. David Norris has received many awards, among which is Credit Suisse Award for Best Teaching. So he was selected by students as the best teacher at ETH Zurich in 2015. He has also received the Max Rösler Prize for which is the highest research prize at ETH Zurich. And he's also an ERC Advanced Grant awardee and a fellow of the American Physical Society, of the American Association of the Advancement of Science, and he also sits on the editorial advisory boards of ACS Photonics and Nanoletters. David Norris is heading an optical materials engineering laboratory, and he and his team are engineering semiconductor and metallic nanostructures to obtain new and useful optical properties. So they study the fundamental behavior of semiconductor nanocrystals or quantum dots, plasmonic films at nanoscale, and they also look for applications of their findings, which are quite many. So today, David Norris will talk about some of them, and he will share some tips and tricks on how to fabricate good quality photonic and plasmonic devices. He'll talk about how to deposit metals, how to pattern metallic or dielectric surfaces by template stripping, and also how to combine these two techniques with thermal scanning probe lithography to produce smooth and wavy metallic and dielectric interfaces that contain an arbitrary number of specified sinusoids. So smooth, patterned, and wavy, tricks and tips for nanophotonic fabrication. David Norris is going to give this 1-hour tutorial. David, thanks a lot for joining us, and the floor is yours.
Thank you. Thank you very much, Anya, for the opportunity to give this tutorial. Let me share my screen here. So, as Anya introduced, I would like to give a tutorial where I basically try to review some things we've been doing over the last years in trying to come up with strategies, hopefully simple strategies, to make nanophotonic structures. And so first, let me just start with a broad motivation. I think in nanophotonics, we're motivated to essentially exploit the power of nanofabrication to create dielectric or metallic structures that can confine or manipulate electromagnetic fields. So I think that in 3 bullet points is what we're trying to do. And so we can imagine that by controlling the shape of some little structure, often called an antenna or nano antenna, that might have gaps or tips or some kind of shape, using that to enhance the interactions with electromagnetic fields and materials and hopefully make useful devices. And so I've mentioned 2 materials, dielectrics and metals. So why dielectrics first? Well, they're inexpensive, they exhibit low optical loss, they are already heavily used, as we know, in photonics and electronics, and patterning techniques are, of course, well established for a material like silicon, which is a dielectric. And they also enable field confinement through essentially total internal reflection, if we think about it, where we can make structures that have resonances as shown in this whispering gallery mode in either a pillar or a sphere, depending on the structure. Now, the downside of dielectrics, of course, is that the confinement that we can obtain, so the size of the field that we can get in the end, is limited by diffraction. And the other material that we're going to look at is metals. Metals kind of have the opposite problem. They are not lossless, so they introduce losses, in some cases significant losses, but they allow much stronger confinement of the electromagnetic fields, in particular because they're not limited by diffraction. So we can consider, for example, with metals, playing with surface plasmon polariton waves. So these are waves that exist at a metal dielectric, in this case air interface, where they're a hybrid wave, a mixture of essentially oscillating electromagnetic fields or light and dragging conduction electrons along with it in the metal. And it's also a surface wave, meaning that it has a field magnitude that's concentrated at the interface and then decays into the dielectric or the metal. And these decay lengths, delta here, can be on the nanometer length scale, so you can confine the field into small volumes. Now, maybe the first question we can address before we move on, and also because it introduces patterning, is how can we generate plasmons, or more specifically, how can we get photons and plasmons to interact or couple? And so we can start with a simple question that we have a perfectly flat metal film and we shine light on it. Can we generate plasmons? And so the answer to that question is no. We can't generate surface plasmons because these photons that come in don't quite have enough momentum to give a kick to start one of these plasmon waves. But what we can do, and this is where patterning comes in, is that we can pattern our metallic film, let's say with just a square wave gratings or grooves. And then when light comes in, we can excite these surface plasmon waves because the pattern itself can make up for the momentum that the photon is missing through diffraction. And we're going to come back to this in more detail in a little bit. So, as many of you know, there's this whole field of plasmonics that's trying to exploit these surface plasmon polariton waves in different contexts. We can just state generally that they're often utilizing man-made metallic surfaces or patterned films, so with some structure on it that's of interest for the reasons that I just tried to motivate, where you shine light on this, you excite surface plasmon waves on the surface, and then you manipulate either their propagation or their confinement in some interesting and useful way. And you can also utilize their hybrid nature, so they have this optical component, meaning that they can communicate with light, so light can generate plasmons or vice versa. And also this electronic character component allows us to confine the electromagnetic fields to nanometer scale volumes. So if we have sharp tips, and I'll show you some real examples in a moment, we can confine the electromagnetic fields in these small volumes around the tips. Now, the main topic, though, of my talk today is how we can fabricate such structures out of dielectrics and metals. And the requirements for our strategies that we try to develop is that they should be as simple as possible. And of course, we want to make the structures be as high quality as we possibly can. So we need to reduce defects and roughness. Basically, it should look like what we want it to look like, because otherwise we'll scatter the photons or plasmons in undesired ways. And use these structures then to control electromagnetic fields. And for the talk today, I'm going to focus on two model structures. I could have chosen several, but just so we have the same examples, I'm going to talk about structures that can create sharp metallic tips, as I've already introduced in my cartoons. And then I'm going to talk about this idea that Anya mentioned of kind of arbitrarily wavy surfaces, either in a metal or a dielectric. And I'm then going to try to address 4 questions along the way that are related to fabrication. So first, it seems kind of like a silly question, very mundane, but actually turns out to be important, is how do we deposit the best possible metal films, for best in terms of their optical properties for what we're trying to do? And then second, how do we pattern these metallic films? Third, I'm going to get into why such wavy surfaces are interesting. It may not be completely obvious. And then the fourth question, we'll try to create metallic and dielectric surfaces that have this arbitrarily wavy profile to them. Okay, so let's start with the first question. So how do we get the best metals? And this question basically turns to what kind of deposition conditions do we use to make our metallic surfaces? And fortunately, a few years ago, I had several people in my group, Kevin McPeak, Sri Harsha Jayanti, and Stefan Kress, who were interested in this question. And so they then went on an exercise to go through the old literature and see what the surface scientists actually said back in the day about how to deposit the best optical metals. And what we learned, or what they learned and told us, is that we were really using non-optimal conditions for depositing our metals, let's say like silver. And it wasn't just our group, but I'm using here as kind of the community. And so these gentlemen then went on to study 4 common plasmonic metals: aluminum, copper, silver, and gold. And they basically restricted their work to a simple thermal evaporator that we all have access to at room temperature deposition, and then collected rules and recipes from these old papers and basically published a cookbook in ACS Photonics. And what they found was really quite interesting in terms of the advantages of the optimization. So first, they showed that you could get improved dielectric functions, which of course is important for everything that we're talking about. In some cases, in many cases, actually better than the literature standards that we often just assume when we do electromagnetic simulations. And maybe important for my talk today is that the metals could be denser, and this led to sharper edges and tips, which I'll demonstrate in a bit can be important. And what was surprising is that all of this came with essentially no additional effort, but just operating the evaporator under the right conditions. And usually this meant to be evaporating with the best possible vacuum that you can obtain, and also to deposit metals at faster rates than most of us were accustomed to, especially for silver and aluminum. Okay, so hopefully now we have good metallic films. How are we going to pattern them? And this again might seem like a silly question, because we can imagine that we want some structure like this square wave grating that I've already shown a couple times. And then we're going to do something interesting with it. For example, put surface plasmons on it. And so you might imagine that, well, the fabrication would be fairly straightforward. We start with a flat metal film that we've deposited, and then we bring in one of the modern tools of nanofabrication, let's say like focused ion beam, and we etch a little trench, and we do that periodically, and we end up with our desired pattern. One could also imagine just using electron beam lithography and reactive ion etching to similarly etch such trenches. But there are several problems with that kind of ideal scenario that I just mentioned. First of all is that when you deposit metals, they're typically rough. So a silver film, when you deposit it, usually has a roughness of a few nanometers, which may not sound like a lot, but when you have surface plasmons living right here at the interface, this can be quite detrimental. The deposited metal films are also polycrystalline, which by itself is not an issue, but then when you go to etch or pattern such a film, all the grains have slightly different orientation and they etch at different rates. And so patterning will actually increase the roughness because of the grain structure. And then finally, to make matters worse, the ions that you're using to etch are actually being implanted in the metal right where the plasmons live. So the metal is no longer pure. And so here is an early example, old example, where we tried to make a bullseye in a silver film. You can see that the silver film was rough to begin with, and then you get these hideous looking trenches when you try to do focused ion beam because of the reasons I just mentioned. And in addition, this kind of approach basically makes one device at a time. Each device is different because of all this grain structure is different. And so we started looking for simple high throughput methods to try to improve this situation. And what we realized is that there was an approach known to make smooth, flat, or unpatterned metallic films, which is known as template stripping. And by coincidence, this was developed almost 30 years ago at ETH Zurich by these 3 gentlemen here. And it was a very simple idea. They took a piece of freshly cleaved mica, and mica can be atomically flat, and they then evaporated a noble metal like silver or gold onto it. Let's say silver. The silver, as I mentioned before, can be rough on the top surface. So if you're trying to make flat metal film, that's not good. But what they realize is that these metals will wet the mica well, so they'll spread on the mica well, but they don't stick very well. So they adhere poorly. So you can bring in something sticky like epoxy, and stick the epoxy to the back layer or the top layer of your silver film, and then strip it off and flip it over. And then this exposed surface that was originally on the mica will be near atomically flat. And so this was known in certain communities as a way to make flat metals, for example, in scanning probe communities, or also self-assembled monolayers on gold, use this template stripping approach. And so a number of years ago, in collaboration with Sengyan Oh, when we were both at University of Minnesota, we decided to look to see if this could, the same approach could be used to make patterned metallic films. And so the idea now was, instead of using mica, to use a silicon wafer where we would pattern some pattern that we were interested in into the silicon. And of course, that can be done extremely well these days with modern nanofabrication tools. Then deposit our metal, just like on the mica. It's rough on the top, but we don't care because we'll bring in something sticky like epoxy and peel it off. And then this surface, which will be a nice replica of the silicon, can have very nice properties. In particular, it can have, where it's supposed to be smooth, it can be rough, have roughnesses of a few angstroms. And all the implanted ions that we were worried about before would be in the silicon because you did all your patterning with reactive ions on the silicon. And then finally, for a metal like silver, which tarnishes, you can leave the film on the silicon template until you want to use it and peel it off, and then you'll get a pristine surface to do your experiments or for your device or whatever. And finally, the silicon template is then reusable, and you can use it hundreds of times if you wish to make all nominally the same structure. So here's a really old example of us doing this, where we took a silicon master template with these circular grooves that were etched with focused ion beam. Then we deposited silver over this whole structure and stripped it off, and you get the inverse of that, of course. So you have these circular bumps or circles on it. And then if I show you this at different angles, you can see that these structures are really smooth where they're supposed to be smooth and patterned where they're supposed to be patterned. And moreover, instead of just making the structure that I just showed, you can really combine this template stripping with other common cleanroom tricks to make sharp tips and edges. So for example, you can use anisotropic etching of silicon, which is a well-known technique. You take a silicon wafer that's oriented in a specific crystalline direction, the 100 direction, and then you mask off a lot of the silicon wafer, meaning you cover it with another material so that you're only exposing the silicon in certain regions. So if I show you kind of a quasi PowerPoint cartoon here, we imagine looking down, we have a mask, and then we've exposed these little circular regions of silicon. It's known that if you dip such a silicon wafer in potassium hydroxide, it quickly etches into the silicon until it reaches the slowly etching 111 planes. And in this particular orientation, you have this fourfold symmetry of the 111 planes meeting at a point at the bottom of this little pit. So you have these little inverted pyramids in your wafer. If you then remove the mask and then do the template stripping off of this, one would expect to get little silver pyramids in your film. And in fact, that's what we did a number of years ago. And this is a 10 micron by 10 micron silver pyramid that goes up to a tip that has a radius of curvature of 10 nanometers. So you get this very precise structure through this really simple kind of deposit and peel off technique. And of course, you get this precision because these surfaces are precise because the 111 planes in a single crystalline silicon wafer are precise. And so just to show this, hopefully over Zoom in real time here, this is a video that Kevin McPeak, a former postdoc in our group, made a number of years ago, where he has a 4-inch silicon wafer that he's patterned, and then he deposited 200 nanometers of silver and stuck it on the back to this gold looking or yellow looking polyamide film. And he flipped it over, and all these diffracted colors here are different arrays of pyramids in his silver film. And then of course, in the background here, the silicon wafer is ready for him to deposit another 200 nanometers of silver and go again if he wishes. Now, in addition to the sharp tips and the pyramids, this same technique can also allow one to make wedges. So instead of having circular openings in your mask, you can basically have slits and make V grooves. Again, very common, well-known trick in clean room. And so if you then do this same template stripping off of these V grooves in the silicon wafer, then you can make such wedges from silver. So this is an array of silver wedges where the radius of curvature of this sharp edge here is 20 nanometers in this case. These structures are interesting because it had been known already from theory that if you do an electromagnetic simulation, there is a very tightly confined mode that exists at the apex and would propagate along this apex known as a wedge plasmon. And here's a simulation of such a mode. This is a 10 nanometer scale bar for the simulation. And so you can see that this wedge plasmon is very tightly confined along this sharp edge. And so now you can start to put different pieces together and make more complicated structure. So for example, maybe on that wedge, we would like these wedge plasmons to bounce back and forth. So we could add mirrors and make a resonator. And so to do that, you can take your V groove in silicon. So this is the V groove in silicon. And before you deposit your silver on it, you can come in with focused ion beam and etch out this extra little trench here across the V groove. And if you then do template stripping on this, you then place basically a little silver block on top of the wedge so that your wedge plasmons will come along this sharp edge and then reflect off of this block. And it turns out that these blocks actually make extremely efficient plasmonic reflectors, so 90 to 95%, with 90 to 95% reflectivity. So just putting all of these pieces together, you can make some fun devices. So this is a device that Stefan Kress made a number of years ago in our group, where we're looking at a wedge from the side. This is the apex, the sharp edge, and then these are these two blocks from the side, and the cavity length here is 10 microns long. And then to excite the resonances of these wedge plasmons in the cavity, we printed 100 quantum dots right here on the apex. We can't see those quantum dots with this magnification, but if I zoom in, here is the apex, and you can see these 100 little quantum dots, these white circles, are kind of huddled together, ready to excite these wedge plasmons. And indeed, if we photo excite these quantum dots, this is the fluorescence spectrum, so his wavelength of the quantum dots by themselves, and they have this red fluorescence line of about 25 nanometers at 630 nanometers. And if we then look at the cavity spectrum, we get these much sharper features. And these are essentially the standing wave modes of these wedge plasmons that are bouncing back and forth inside this cavity. And in fact, with the white curve, you can well reproduce the data just with a Fabry-Perot model, basically two parallel mirror type model from optics. You can reproduce what we observe. And all of this can be obtained because you basically have a really simple way to make a very high quality, precise structure. Now, just to demonstrate that the quality of the silver matters. So this metal deposition that I said that we optimized, if it's not optimized, it affects the plasmon propagation. And one can see that if you look down on such a wedge, this is a spot of quantum dots that's glowing into the microscope, but it's also launching wedge plasmons, which are leading to these streaks of photons as well. The wedge plasmon is leaking to photons, which is causing this streak in the microscope. And if you plot the intensity of that streak as a function of distance, you get this exponential decay, which you can use to figure out how long these wedge plasmons are propagating. This was with our optimized metal deposition. So for silver, if we use kind of conventional deposition or what we had been doing before, I mentioned that the edges weren't as dense and you get all this porosity and you can see all this defect scattering. And if we were trying to fit an exponential decay to this type of curve, obviously this would be problematic. And so this simple fine tuning of the evaporator, according to the old surface scientists, really makes a big difference. Now, beyond noble metals, template stripping tends to be useful for lots of things, and we've made a little bit of a cottage industry out of it. You can start with your silicon wafer that's patterned, and instead of depositing just the metal you want, you can put a very thin layer of gold down, and then put any desired material you want, as long as it sticks to gold. And you could put different layers of materials as long as they stick together into gold. And then bring in something sticky and strip it off, the gold will detach from the silicon template, and then you can selectively etch away the gold and you leave behind this new desired material that maybe wouldn't template strip by itself. And a good example is a refractory or thermally stable metal like tungsten. We had a project on thermal photovoltaics a few years ago, and we wanted to make arrays of little 250 nanometer tungsten pyramids, and tungsten is a very difficult material to pattern. But using this trick I just mentioned with template stripping, we could get very nice patterned tungsten surfaces. And then we kind of demonstrated that this could work for many materials, so tantalum, silicon, cadmium sulfide, and then this is indium tin oxide. And so these are all sputtered, but using this thin layer of gold that's then removed in the last step. And then finally, more recently, we've used template stripping on solution processable materials. So these are some colloidal quantum dots that were basically deposited in solution, then filled a silicon template that had a little ring in it. And then when we strip it off, we get this little micro ring of quantum dots that we've demonstrated as a micro ring laser. Okay, so those were the first two questions. So I tried to address how to get good metals and then how to pattern those metals via template stripping, and then also demonstrate that template stripping can actually be used to pattern dielectrics and other materials. And now I want to go on to address why one might want wavy surfaces. And so for this, we can consider diffractive surfaces in general. So, and the example we've been using is square wave diffraction grating. And we all know that if a beam of light hits such a diffraction grating, its direction can be altered due to diffraction or essentially due to interference. And we can consider how that happens through looking at momentum conservation. And in particular, if we have a grating that has a period capital lambda, this gives rise to what's known as a grating momentum vector, which points in the direction of the periodicity, which in my cartoon here is along x, and has a magnitude of 2 pi over this period. And so if we consider the in-plane momentum of this photon that's coming in addition to reflection, which we know for reflection, just the angle of incidence equals the angle of the output, so that the in-plane momentum or wave vector, which is our stand-in for momentum, is just the same. We will also have the possibility of diffraction. So if we restrict ourselves to first order diffraction, we're basically adding or subtracting 1 unit of this grating momentum vector g. So if we add 1 unit of g, we will make the beam diffract towards the surface interface. And if we subtract 1 unit of g, we will make the beam diffract towards the surface normal. And of course, the angles of these diffracted beams will be wavelength dependent, which is why, of course, we use diffraction gratings in spectroscopy. And so all of what I've just said here, of course, has been known for an extremely long time. And diffraction gratings have such a long history, in fact, that you can find these really amazingly fun papers like this one from 1786 entitled An Optical Problem Proposed by Mr. Hopkinson and Solved by Mr. Rittenhouse, where these two gentlemen were talking about fine threaded cloths and their diffractive properties. More recently, and maybe relevant for us, is that maybe starting a century ago or so, metallic gratings, which were mechanically ruled, or basically grooves were scratched in a metal surface, started to be used for spectroscopy. Now they're much more commonly lithographically etched, where you etch these grooves. And again, the key parameters are the same. You have a periodicity, a spatial period, which sets the momentum contribution that is going to be useful for your diffracted beam. And so this suggests that if we control the spatial frequencies in our interface, that we can control the diffraction of the impinging beam. And moreover, Fourier optics gives us a very convenient way to look at this, in the sense that the surface profile, the height of the surface as a function of x, how the surface goes up and down as a function of x, is related to the spatial frequencies, or these grating momentum vectors g, in the surface through a Fourier transform. And so we have this connection between the surface profile and the momentum that will come into our diffraction through this Fourier transform pair of position and momentum. Again, Everything I've told you here is known. I haven't told you anything that's new. So what's the problem that we're trying to address? And the problem is that due to fabrication, we're typically limited to only 2 etch depths in our surface. So as I've shown in all of my cartoons to this point, we have 2 etch depths, meaning that the surface is either etched or it's not etched. And so here is this SEM electron micrograph that I took from the internet showing such a grading. And of course, this constraint constrains the surface profiles that we can get. And this may seem like a trivial problem, but it actually limits what we can do with our diffractive surfaces. And in particular, it leads to 2 issues. So first, it's going to give us unwanted spatial frequencies in our surface. And I think this is clearly seen if we just consider a square wave grading, and we know that such a periodic structure, its height profile as a function of x, can be written as a Fourier series where we have a series of cosines, each having an amplitude a spatial frequency g, and a phase phi. So in that case, of course, our grading will contain the fundamental spatial frequency that we presumably care about, as shown here, but it will also have to contain many other sinusoids to make up these sharp edges, as we know from Fourier series. Each of these additional sinusoids will have an amplitude, spatial frequency, and phase. Each can potentially contribute to the diffraction. And so we will essentially lose control of the Fourier components in our surface, the spatial frequencies, and this will mean that we lose control of the diffraction. The second issue that comes up is that we are allowed a limited number of desired spatial frequencies. So the first one was we had too many that we didn't want, but we also have a limited number of spatial frequencies that we want. And this, I think we can see if we imagine a problem where we have a waveguide and we want to add a diffractive surface to that waveguide and send in red, green, and blue photons, let's say all at normal incidence, and couple them simultaneously into the waveguide. In other words, we want a grading coupler, couple red, green, and blue photons all at normal incidence. Now, to do this with our diffractive surface, we're going to need to be able to control 3 spatial frequencies simultaneously, which with only 2 etch depths, this is extremely challenging, if not impossible. And so these 2 issues, having unwanted spatial frequencies and not being able to control the ones we want, how are we going to try to address these 2 limitations? And so essentially, we would like to better engineer the Fourier spectrum of our surface. And this, again, is not a new problem that I'm telling you about. This is a recognized problem, and people have come up with clever solutions to try to work around it. One solution is just to live with having only 2 etch depths and just be clever. And so, for example, one can make not periodic grooves in your grading, but aperiodic grooves. So here's an example from Jerome Feist's group at ETH, where looking down on a grading where they've used the groove spacing is aperiodic, as you can see here. And this aperiodicity gives an additional knob to control the Fourier components or spatial frequencies in the surface. Another approach is to make these so-called metasurfaces, where the Capasso group at Harvard has really been a driving force, where you use your 2 etch depths to make little local blocks. These little blocks act as sub-wavelength resonators so that when a light beam comes in, its local wavefront is affected. And then collectively, all these little blocks can do something interesting in terms of the diffraction. The second approach is to try to go beyond 2 etch depths and make multi-level surface profiles. And so, for example, you can use what's called interference lithography, where you interfere several beams in a photoresist to make a wavy interface. There's also several tools, or a class of tools known as grayscale lithography, which try to get at multi-level surface profiles. These kind of approaches are powerful in principle, but so far they've really demonstrated insufficient control to do what we imagine doing, which is to be able to make arbitrarily wavy surfaces. And so in this case, we would like to make what we've been calling optical Fourier surfaces, where you really have some wavy profile, where you can describe the height h as a function of position x here as this Fourier series of sinusoids. And you can arbitrarily control the surface pattern, which allows one to have many desired spatial frequencies where you control each of their amplitude and phase and eliminate all the unwanted spatial frequencies because you've controlled exactly how the surface is modulated. And then the dream would be that this would allow one to make more sophisticated diffractive surfaces because you have more control. Okay, so if this is the vision, how can we fabricate this? And so the technique that we've been using that Anya mentioned is thermal scanning probe lithography. And this was a project that was really driven by Nolan Lassaline, a doctoral student who's about to finish. And the way this technique works is basically you have a hot tip on a scanning cantilever. And then by bringing this tip close to a thermally sensitive polymer film, and then raster scanning this tip in X and Y, so in the plane, while controlling its depth in Z, and basically burning away the polymer as you move, you can carve out a very precise profile in the polymer film. And what's nice is, since this is essentially a fancy AFM, you can measure topography as you go along and use that for feedback to kind of refine the pattern as you go. And the capabilities of this approach in the hands of the people that developed it at IBM Zurich, this is a paper from Armin Knoll's group, they could get sub 10 nanometer lines, so spatial features in X and Y in the plane. In our work here, we're going to restrict ourselves to above 100 nanometer spatial resolution in plane, but we are going to utilize the fact that you can get amazing control in the height of your profile, so in Z. And so I'm going to show you some patterns that have below 2 nanometers root mean squared error on their height over a whole pattern. And it turns out this is a fairly simple and flexible approach for what we're trying to do. And one huge advantage that I've already alluded to is in terms of Fourier optics, is in terms of design, because we can take the Fourier transform of the desired output we want. So in other words, if we know which momentum contributions we want in our diffraction, then we can use a Fourier transform to get an analytical surface profile or height function of our surface. And we can then take this analytical function for our profile and we can convert it to a grayscale bitmap, where at each pixel in the bitmap in X and Y on the surface, it will tell us, it'll tell the tip what height we want for that particular pixel. And this bitmap is then fed into the tool and we can see how it works. And so this first example that I'm going to show here is a single sinusoid. So we have a height profile that just goes as this cosine here. And so the bitmap that's generated from that would be looking down on the surface. We can see that the surface is modulated in height in X and then is constant in Y. And this particular bitmap had 10 nanometer by 10 nanometer pixels and 256 depth levels, or 8-bit. Okay, so then Nolan took this pattern and tried to pattern the polymer resist. We can see what happened. He did this over a 10 micron by 10 micron pattern. And this is the measured topography that he made in the polymer. So again, the height profile goes up and down. This is the height color map here. And the structure is constant in Y. This is again looking down on this modulated surface. And if we look at a line scan through the structure, then you can see how well it's really reproducing our targeted function. These open circles, if I blow this up, these are the measured depths of our profile. And then in the red line is our targeted function. And in fact, over this whole pattern, the root mean squared height error of what we got from what we wanted is 1.8 nanometers. So really you get very high fidelity patterning from this approach. Now, of course, we don't want to just fabricate things, but we want to know how they perform in terms of their optical response. So we want to take this polymer and replicate it in other things. And so we can start with just metals, and then we can turn to our old friend of template stripping and see if this can replicate that polymer surface. So in other words, taking that polymer interface and evaporating silver on it instead of a patterned silicon, and then again, bring in epoxy and a piece of glass and template strip it off, and then to see if we can get a nice wavy silver surface. And this would also allow us to reuse the polymer template, just like we reused the silicon template before. Okay, so does this work? Well, it turns out that Nolan demonstrated that it works extremely well. So here's looking down on a wavy silver sinusoidal surface that was made from the polymer. And I can zoom in on this, and the structure that you do see here are just the grains in the polycrystalline silver, but the surface itself is smooth and wavy, as can be demonstrated if you take this surface and put it on an atomic force microscope. Again, you see the measured and the targeted values match extremely well. Now, of course, this was just a simple first example. You can go beyond a single sinusoid, and the next baby step is to do 2 sinusoids, 2 cosines. And so this is looking down on a double sinusoid. This is, again, the measured and targeted surface profile matching extremely well. Or you can add a 3rd sinusoid and make this triple sinusoid in silver. And again, you get exactly what you wanted to get in the output. And of course, one of the points is that we control all of these parameters. So the amplitudes, the spatial frequencies, and the phases of these 3 components in this case are all controlled. And so now we can start to think about what we can do with this. And I'm not going to answer this question completely. I'm just going to show you a few first simple examples. And the first is maybe the most obvious thing, which is to see how these act as a diffraction grating. And so Nolan could look at the simple question of, he made a wavy surface and sent in light at normal incidence. And in first order diffraction, we should diffract some light to the right and some to the left. And so how efficient can these diffraction gratings be? And so he made such a structure. Now the structures had to be deeper to make efficient diffraction gratings. And he measured the diffraction efficiency as a function of wavelength for such a surface. Ignore this dip. This is due to coupling to plasmons, and we'll just look out here in the red. And we see that basically 50-50 goes to the right and to the left, as we would expect for such a symmetric structure. And in fact, if I add both of these together, we get essentially 100% diffraction efficiency. Now, you may want to now use your design aspect, though, to make all the light go to the right. And so it's known that a sawtooth grating allows one to do this in theory at 100% efficiency. And so Nolan took the first 2 Fourier components of the sawtooth grating and made such a structure, again, deep enough to make it efficient in terms of diffraction. And indeed, he essentially sent all of the diffracted light to the right, which can be seen if we add the 2 components together within our experimental error. Again, we get near unity efficiency. So this showed that this design aspect could really be used to make efficient unidirectional diffraction. And the second simple example is to make a multi-wavelength plasmonic coupler. So going to that example I said before for a waveguide, we can now imagine, can we send in red, green, and blue light at normal incidence and couple the surface plasmons all at the same time? And so Nolan designed such a surface to do that, that has 3 spatial frequency components, and then measured light coming in at normal incidence, the reflectivity of that light, so as a function of its wavelength. And indeed, he saw these 3 dips as he designed, which is coupling simultaneously red, green, and blue light at normal incidence. And the efficiency of these dips, as far as we can tell, is state of the art in terms of this multi-wavelength coupling. And finally, maybe the third example before I move on to the last little bit is we can also now imagine not just diffracting light off and diffracting light into a surface, but now we can use the waviness to affect propagation. And so just one simple fun example of this, something that Nolan did, is he made plasmonic stop bands in the following way. So he designed a surface so that photons coming in at a slight angle, the surface would have a frequency component that would allow that photon to couple to a surface plasmon, let's say going to the right. But he also had the surface include a second spatial frequency component that would couple right moving plasmons to left moving plasmons and vice versa. And since plasmons could no longer propagate because they'd be constantly diffracting back and forth, this opens up what's known as a plasmonic stop band. And so he designed such a surface that had these components, And moreover, he fabricated a series of gratings where the only thing that he varied was the amplitude of this G2 component in the surface, which opens up the stop band. And here is a GIF combining all of his experiments. So each of these frames in the GIF is a different experimental structure. And you see that both the measured and the targeted function gets more complicated as this A2 component turns on. And simultaneously, if you look at the photons, their energy going in as a function of their in-plane wave vector or momentum, these red streaks are photons that are coupling to plasmons. And as this A2 component turns on, you get this stop band that opens up basically due to this diffraction back and forth, or left to right and right to left. And this basically is a simple example to show that wave propagation in the surface can also be controlled by controlling the Fourier spectrum. Okay, and so in the last few minutes, beyond one-dimensional periodicities, of course, is also possible. We're not just limited to linear sinusoids, but we can have radial sinusoids, or we can chirp the frequency and make, in this case, a zone plate in silver. These are still essentially 1D, though, because they're circularly symmetric. But one can really start to play with the two-dimensionality of the surface. So you can start overlaying sinusoids. So looking down, you can imagine having one sinusoid that's periodic straight up and down here, and one that's tilted by 10 degrees. And when you overlay such a structure, you would expect to get a Moire interference pattern, which is exactly what you see in your surface. So in this case, G1 for the first grating and G2 were rotated by 10 degrees. If we rotate it by 40 degrees, then of course the interference pattern changes. And then finally, you can go to even higher rotational symmetries by combining more. So if you combine 3 sinusoids, each rotated by 60 degrees, you get a hexagonal pattern. This hexagonal pattern here is in the polymer. So this is a measured structure, and then replicated into the silver. Or Nolan went on to combine 6 sinusoids, each rotated by 30 degrees. And in that case, you get a quasi-crystalline pattern. Again, this is measured in the polymer, and then this is replicated in the silver. And I don't have time to show it, but the optics, if you send light and bounce off of these surfaces, you see only diffraction due to these 6 components in your surface. So you get exactly, no matter how complicated it looks to us, the photons see exactly the spatial frequencies that we put there. And then finally, we can make dielectric surfaces from our, I've shown you just metals so far, but we can also make dielectric surfaces that are wavy, either using template stripping, where instead of depositing metal on the polymer, we now deposit a dielectric and then strip it off. Or one can take our pattern polymer and simply transfer it to the substrate, which is a dielectric, by etching, and then you'll have a wavy dielectric pattern. Which one to use is you have to have, that you can decide by several factors. First of all, template stripping is just really easy, so it's usually our first thing to try. But because etching typically needs optimization, but it also allows one to potentially amplify the depth of the profile, and so this has some advantages. And so just to show one example, we've made silicon, silicon nitride, and titanium gratings. And this is just one crazy example that Nolan made, combining 12 sinusoids to make this silicon quasi-crystalline pattern. But I think this is just the beginning. So in conclusion, I've tried to show you some simple steps to make better metals and well-defined structures that can incorporate sharp tips and edges. And I should mention that Sengyan Oh, our collaborator, has some independent work where he's made some amazing gaps. So this is also possible. And then I tried to demonstrate these wavy diffractive surfaces in both metals and dielectrics. And of course, since we also in our group make quantum dots, we're often combining these with quantum emitters, which I didn't discuss at all. So finally, let me just acknowledge the people that did the work on the metals and the wedges. Kevin McPeak and Stefan Kress were driving forces, along with many other people that helped. And then on the wavy surfaces, Nolan Lassaline was a driving force, again, with lots of people to help. From Swiss Litho, or now Heidelberg Instruments, we had lots of help on the thermal scanning probe lithography from Martin Spieser and Samuel Bissig. And then the template stripping project really started through a collaboration with Sengyan Oh and 2 great students, Prashant Nagpal and Nathan Lindquist at University of Minnesota. So let me stop there, and I'll be happy to answer any questions if there are any.
Thanks a lot, David. This was a great talk. So we already have a couple of questions. So the first one is it possible to create pattern film on non-flat surface like optical fiber? This is a question from Nirmal Punjabi.
Yes, so it is possible to do the template stripping on curved surfaces. And we've done a little bit of work on that, but we haven't really had a strong motivation to do that. I think Seng-En Oh, my collaborator, and some of his own independent work did a little bit more than we did. But I mean, it's all just playing with what the substrate is and if it's pliable and things like that. On an optical fiber, yeah, this would also presumably be possible. It has been something that we've done though.
Okay, thanks. And another question is from Juan Luis Garcia Pomar. He says that it's a very nice talk, and he's asking, usually, which is the thickness of the metal that you remove from the template with epoxy?
So typically we just want our films to be optically opaque. And so in the case of silver, we usually deposit, 250 nanometers-ish or something like this. It could be thicker, it could be a little bit thinner, but this is just the ballpark. For the use of template stripping for making other dielectric structures or whatever, then we use this thin layer of gold. The gold can be very thin. I mean, gold is much more forgiving in the deposition than silver. So you can make 10, 20 nanometer thick layers of gold that are very flat and then can be used in this way. So, and for gold structures, you could get away with making it thin and even semi-transparent if you wanted that for some reason.
Right. I actually have a question of my own. So when you do the template stripping, is there any mechanical stress introduced in the metal? Does it impact the structure in any way?
Yeah, so this is a great question that I get asked every once in a while. And to be honest, presumably there is some stress, of course, that's being applied. We've never really looked at this too carefully. So I don't really know the answer to it. I think it's a great question, and we haven't seen it impact kind of the things that we want to do, but there might be certain applications where this is important.
Right. And so where are you going to, like, is there any further work where you're going to take these smooth wavy surfaces next?
Yes, so I mean, there are a lot of things now that one can imagine doing with them. If you have a surface that can make a better diffraction grading, that can make a better coupler, that can control how waves propagate on a surface, this certainly has implications for, let's say, photonic integrated circuits or other types of devices. But I think beyond that, there are going to be other implications and things that we're working on that I don't want to talk about.
Sure.
That will mean that this technique is more broadly interesting.
Okay, so we have another couple of questions. So from Luis Perez, he's saying that you said that the size of the pattern was 20 times 20 microns. What's the effect of the size because you have very huge unit cells?
Sorry, I don't understand the question.
Yeah, I'm not sure. So probably, I'm not sure what.
Maybe he can chime in and.
Yeah, exactly. Luis, I will, let me find you and I will give you the right to speak. So if you want to jump in the discussion now, you can do that. Okay, so
here.
yeah.
Hello.
Yes.
Well, thank you, Professor Norris, for your very good talk. My question was, when you are overlapping different kind of patterns, you have effective unit cells that is very big. And you said that your patterns were 20 per 20 micron size.
Yes.
So which is the effect of the size? For example, instead of having 20 per 20, you have 100 per 100, you will change the effect or not?
Yes. Okay. So I understand your question. So it's a very good question. So indeed, since we have finite size structures and we're overlaying different periodicities, let's say, that we might not even have a 1 unit cell. I mean, the unit cells can become quite big if you overlay to slightly different frequencies, for example. So for the most part, we haven't seen that affect anything other than we do see finite size effects in general, that as the size of our structure, which is periodic or periodic over some longer length scale, but let's say it's 20 by 20 microns, we do see some broadening, for example, due to finite size effects, but we don't see any extreme effects. But presumably if we made it smaller, even smaller, we'd be able to study these types of finite size effects. But you're absolutely correct that the units, we might not even have a unit cell depending on what we're overlapping in these patterns.
Okay, thank you.
Okay, so we have another raised hand. So Alexander Leitis, you can ask your question now. Okay, so maybe in the meantime, then Deepa Gendani is asking, is it possible to make robust and hard pattern polymer? And if yes, which material is good for it? Can we use it, for example, for PMMA or PDMS?
So, and this is in the context of the wavy surfaces, I presume?
I'm guessing, I'm not sure.
So Nolan actually patterned into the PMMA, so this is certainly possible. It depends on what you mean by a hard polymer. I mean, certainly you could try to use the PMMA pattern that he made and use it as a template and cast maybe another harder polymer or cross-link polymer or whatever onto it and then try to detach it. None of that we've done, but you could certainly imagine doing that.
Right, so Deepa asks that it's a standalone polymer without any substrate.
Sorry, does it?
Standalone polymer without any substrate.
Yeah, so I mean, if you cast something on the surface that you've patterned and it's thick enough to be mechanically stable, then you could detach it and it would be standalone. Mm-hmm. Of course, you have to satisfy that it's mechanically stable. So there would be limits on how thin it could be, but that would certainly be possible, yes.
Okay. Okay, so if anybody else has questions, so someone really liked your talk in the chat. Yeah, if there are 3 more minutes that if someone wants to ask something, maybe from the panelists, you can raise your hand and you can ask something. Yeah.
Yes, I have a question. So thanks for an excellent talk. I was wondering, when you do the template stripping and you, for instance, deposit gold and you say that it's compatible with other metals, do you ever have problems with like intermetallics forming?
Yes, so you're absolutely right that there are some constraints that one has in this process. And for example, things have to stick to certain things and not stick to other things. That's one constraint. And when you deposit the layers, let's say on top of each other, then you can't have a lot of interdiffusion, as you mentioned. So the examples that I showed, none of those issues were a problem. So let's say we wanted to make a tungsten array. Tungsten is difficult to pattern. We put a thin layer of gold and we sputtered tungsten on top of it. The tungsten stuck to the gold enough that when we tried to peel the 2 layers off with epoxy, the gold detached from the silicon rather than the gold detaching from the tungsten. So, but you're absolutely right that those kind of real world things that you have to worry about when you try to put these things together.
Thanks.
Okay, great. Thanks a lot. So I think we can move to the next presentation. Thank you, David. This was really great. Thanks a lot.